In this lesson, I thought we'd take a look at trying to kind of clear up some ambiguities that exist between the US system of measurement and the metric system. And I got to this because I was looking up I was trying to find the volume of a train car, a hopper, and it just kind of landed me on a Wikipedia page that was discussing about tons. You know, we all know in America 1 ton is 2,000 pounds. Probably everybody knows that. Okay, but it also said at the same time that 1 ton is equal to 907.18474 kilograms. Well, that kind of raises a red flag for me because that really isn't a direct conversion like this. And I'm going to show you what I mean in a second if you're not familiar with this. And then it also lists the metric equivalent. This is sometimes called this is called the short ton in the US, but in the, so if you're in Europe, 1 ton is actually 2,204 pounds, and it's also 1,000 kilograms. Again, this shouldn't be a direct conversion because these really aren't equivalent type units. Because in the US system, pounds includes the force of gravity, whereas kilograms in the metric system does not include the force of gravity. So really, we'll try and see how they actually arrived at this number in this sense. So let's say, for instance, you put a little object up here in space like this, right? And we're looking at, this is the positive z-axis up here like this, z, and here's our ground down here like this. All right, and if we said maybe this was our 2,000 pound object right here, and well, if you put it into space, 2,000 pounds implies that it's already feeling the effects of gravity, and it will fall to the ground like this. All right, so that's one thing, because it has gravity is implied with this pound unit of measurement. However, if you put, in this case, this 1 metric ton up here, but if you put 1,000 kilograms up here like this was your same thing, and this is 1,000 kilograms, because they're saying it's the same thing, that a ton is a pound, so we might as well call it 1,000 kilograms. Well, if you put that 1,000 kilograms up here in space, well, essentially that thing's not going anywhere, because that's a mass measurement, right? In order for mass to have weight, see, this pounds is a weight measurement, but this is a mass measurement. In order for kilograms to have a weight, it has to be multiplied times the acceleration gravity in metric units, which is 9.81 meters per second squared. Let's see if I can just put that up. So it's 9.81. Oops, yikes. Hang on, 9.81. We don't need 2 of those guys there. 9.81 meters per second squared. And we put a little 2 up here like this. All right, so if we multiply 1,000 times 9.81, so we'll multiply that times 1,000, then we get 9,810. All right, let me get rid of this one extra digit like this, so 9,810. But suddenly that becomes a weight, but it's not a weight in pounds. What it becomes is a weight in, let me write this down, newtons. Like this. So that would be like the equivalent of what a pound is in the US system, except I want to know what this is in pounds. See, because this says it's 1 ton is 2,000 pounds here. Well, we'll use this measurement here because really that's what we're looking after. So really this is saying that 1,000 kilograms is equivalent to 1,000 kilograms is equivalent to 9,810 newtons, but then we have to get newtons into pounds. So here's another conversion factor. Okay, so now we have 1 pound of force is equal to 4.44822, etc. newtons. So that's the conversion factor we need to do to get this from newtons into pounds. So obviously if we have 9810 like that, it looks like we have to divide by 4.448222162 equals. Okay, what happened? Okay, let's pop that off the stack. Let's pop that, swap that, and divide. All right, so there's probably 9,800. So we swap that off the stack, so now we have 9,800 pounds, 9,800 newtons divided by this 4.48 newtons in 1 pound, and that gives us 2,205. So there's some precision missing somewhere, and that's how you end up with 1 ton being equal to this many pounds. So there's no direct conversion like the cited implied, but this is actually common. It's standard for people in the US just to go from, unless you're a scientist or engineer, they know all about this stuff, but if you go from, otherwise we just kind of interchange. We go, oh yeah, we say it weighs so many pounds or it weighs so many kilograms, but kilograms is not a weight. Kilograms is a mass, and it has to be multiplied by the acceleration of gravity, 9.81 meters per second squared, in order to become newtons. And newtons, remember, is a weight. It's kind of like pounds is a weight, and where in the US you know about, if you make a woman mad and she takes her high heel and stomps on your toes, we say it's like, with that little square piece like that, she's pounding down with, so many pounds per square inch. However, in the metric system, you pound down with so many newtons per square meter. So there's some differences in that. All right, well, it's kind of a confusing topic, but maybe it makes a little bit of sense. All right, well, that's it for this lesson, and I'll see you in the next lesson.